Hello again, everyone, and this is the Mars Reconnaissance Orbiter Mission Science Briefing. Here to talk about the mission, we have Michael Meyer, the Mars Exploration Program Chief Scientist from NASA headquarters, Richard Zurich, the MRO Project Scientist from the Jet Propulsion Laboratory, Alfred McEwen, the Principal Investigator for the High Resolution Imaging Science Experiment from the University of Arizona, Scott Murchie, the Principal Investigator for the Compact Reconnaissance Imaging Spectrometer for Mars from the Applied Physics Laboratory, and Enrico Flamini, the Director of the Solar Systems Programs for the Italian Space Agency. And we'll begin first with Michael Meyer. Mike?
I have to tell you that I'm very excited to be here. We're getting ready to launch the Mars Reconnaissance Orbiter. This is an extremely sophisticated spacecraft that's going to follow our Follow the Water theme that the Mars Exploration Program has been using. And it's going to look at the atmosphere, at the surface, and also in the subsurface. So one of the things that the Mars Exploration Program has been looking at is 4 different objectives. One is whether or not life ever started on that planet, if so, or if not, why not. Looking at the climate, how that has evolved through time, and understanding how that's played a role in the planet itself. And then looking at the geology, see how the planet has evolved and its interaction with water. And then last but not least, looking at what kind of resources may be available and also perhaps what hazards might be there on Mars for future explorers. So within this, the Mars Reconnaissance Orbiter plays a very grand step in our exploration of moving us toward understanding the planet on these scales, using water as sort of the cross-cutting theme. And what I'd like to do is give you an example of how we're progressing on this. We've alternated between having orbiters give us a global view of the planet and identifying certain interesting areas to sending landers that then look in place at that particular area and make the measurements that surprise us, inform us about what we thought we knew from a global scale, and then we feed that back into what we should be doing with the next orbiter. So following along that line, what I'd like to do is show you the first slide that gives you a picture. This is Mars Global Surveyor, and during that mission, the thermal emission spectrometer identified perhaps the only region on Mars that we could tell at that scale that indicated there might have been water on the surface of the planet. And this is the Meridiani planum, and what's colored in green is the mineral hematite. And what that did was it made us very interested in sending a lander there to explore it. So if we see in the next slide, this is a picture of Eagle Crater. This is where Opportunity landed, and amazingly enough, fell into this small crater that's only about 20 meters across and found an outcrop and learned through that exploration in that one spot that there is water on the surface of Mars. Now, one of the things that's going to be very interesting about the Mars Reconnaissance Orbiter, with its spectral resolution and its spatial resolution, we're going to be able to look at a spot on the size of Eagle Crater and identify that there might be a mineral associated with water in that spot. So we're going to move from, with the Mars Reconnaissance Orbiter, looking at things at a global scale, but able to identify things on such a small scale that we can now know more intelligently where to send the next landers, such as the Phoenix Scout mission in 2007 and the Mars Science Laboratory in 2009. So it's going to feed very much into the science that we learned about the planet, and we've progressed that way, but also the Mars Reconnaissance Orbiter is really going to play a role also in identifying landing sites and characterizing them, telling us whether or not they're safe and how interesting they are. And also, as we heard in the previous press conference, it's going to play a very big role in communications for surface-landed access as we go forward in Mars exploration. So with that, I thank Chuck and turn it back over to you.
All right, Mike. Now to Richard Zurich, the MRO Project Scientist from JPL.
Thank you. There were 8 science investigations that are selected for the MRO mission. With this selection, NASA made a commitment to improve the resolution and the coverage at high resolution of what we can see on Mars. We want to see the details of both the surface composition and of its structure all the while that we're also monitoring the atmosphere and learning more about the present climate. Now, you're going to hear more about the imaging spectrometer and our high-resolution experiments in just a moment. We also want to look and to follow up on a discovery that the Odyssey spacecraft made, that there is ice present in much of the upper yard or so of the Mars surface over much of the planet. Now, it's not everywhere, but it is extensive, and we want to know whether or not that layer of ice is just a thin layer that's in equilibrium with today's atmosphere, or whether it represents just the tip of an iceberg, so to speak, a cryosphere that extends much deeper. And so the Italian Space Agency has provided to NASA for flight a radar that will look at the near subsurface, complementing the radar that is being flown today on Mars Express. We're looking for that things near the surface, deeper than a yard, up to a mile deep into the surface, depending upon what the materials of Mars are like. As I said, you'll hear more about these investigations from the principal investigators and people involved in just a moment. First, let me talk about the other experiments that you'll not hear from today, but which we'll talk about particularly as we get to Mars orbit insertion and aerobraking at the planet. If I could have the first slide, please. Many of these instruments focus their attention on the atmosphere and understanding the present climate, including the seasonal cycles of where water vapor goes on the planet and dust. Mars does an interesting experiment for us. There are times that local clouds become regional dust storms and even global, as seen in this image, where you can see this is the same side of the planet, and the markings that are on the left have disappeared here for you on the right. That's disappeared under a global haze of dust. Why does the planet do that? And why does it do it in some years and not in other years? And what do these mechanisms mean over the long term for the layered terrain that we see on the planets, particularly in the polar regions, where we hope someday to explore those, to understand them, and we can do that from orbit with our MRO as a start to that process, to understand the physical history that's recorded in that layering. If we can go to the animation now, I'll show you some of the places on here where we've got the instruments working on the spacecraft, and in the animation we'll show you that, but I want to remind you that we also have two facility experiments that use the spacecraft itself as the instrument. By recording the variations in density as we go through aerobraking, we understand more about the upper atmosphere. With the CTX camera, here in yellow, this would be high resolution on another spacecraft. For us, it's the moderate resolution and gives context by covering more area at high resolution than we've had before. In the middle here, you see our atmospheric sounder that measures the temperature, tracks the dust and the water vapor in the atmosphere. Over on the left, you see our weather camera that will trace not only the clouds and dust clouds and storms and ice clouds, but also ozone in the atmosphere. In the back is the 30-foot antenna, which is the radar antenna, as it probes into the surface. The red is the imaging spectrometer, that is our mineral detector on the planet at spatial resolutions that are unprecedented. And finally, we have our high-resolution experiment, which will be able to zoom in a foot per pixel is the scale of those, resolving things that are a meter or a yard across so that we can look at the surface in much more detail than we've been able to do. Now, we have our two facility experiments, and as I said, one actually gets started in aerobraking itself. Uses a spacecraft and its motions that's perturbed to map out the structure of the upper atmosphere. We need to know that for future missions as we fly them into the atmosphere, but we also want to know how the mass of the atmosphere may leak out into space. Water may have been lost over time on the planet and is no longer present where Mars once had a wetter early history. Our other experiment looks at the gravity field itself, and we can look at it with such precision that we can trace the exchange of mass between the atmosphere and the surface. Mars does an interesting experiment in which 25% of that atmosphere freezes out in a seasonal cycle in the winter poles. Our other two instruments we've talked about very briefly here, the sounder and our weather camera together, form the climate experiment and continue a record that began with Mars Global Surveyor. Moving to our surface instruments and probing into the surface, I'll turn this over to Alfred McEwen, who will talk about the high-resolution imaging experiment on MRO.
Right, Alfred McEwen, the principal investigator for the high-resolution imaging science experiment from the University of Arizona. Alfred.
Good afternoon. The HiRISE camera is a magnificent instrument supplied by Ball Aerospace, who produced a very high-quality instrument for us. It's basically a big digital camera, only this one has a primary mirror that's 1/2 meter in diameter, about this big, and that will be the largest camera ever to leave Earth orbit, largest telescope. And it's also a gigapixel camera, or 1,200 megapixel camera. So to see all of a high-rise image at full resolution, you would need 1,200 of your typical computer monitors stacked up. If I could have the first slide, I'll show you a view of the high-rise telescope. There's a half-scale model, by the way, sitting on the table here as well that you could look at. But here is the full-scale image of the telescope with some people for scale. It's actually a little misleading. That makes high-rise look even bigger than it really is. But it's big. Everyone agrees about that. Here it is. It's hanging from cables, and this is as it's being installed on the MRO spacecraft last December. The cover on front there with the red stripe, that has now been removed. That's a cover over the aperture. In the back of this telescope, we have our focal plane system. We have a total of 14 CCD detectors. So this is like 14 cameras flying in a close array. And these have 10 across the field of view in black and white, and some extra ones in the middle to provide infrared color. So how does the imaging from HiRISE compare with previous Mars cameras or current Mars camera? The best camera currently orbiting Mars is the Mars Orbital Camera on Mars Global Surveyor, which has revolutionized our understanding of Mars. HiRISE will be about 5 times finer pixel scale than the Mars Orbital Camera. So to give you some idea of what this might look like, we've made some simulated images of the Grand Canyon for what it would look like with HiRISE and made a degraded version. So this first view here is the degraded version that might be similar to what the Mars Orbital Camera would see if it were zoomed in on a very small area. And we can clearly see layers. We can see very large blocks, interesting things. In the next slide, we will see the HiRISE view, and I hope your monitor is good enough to appreciate the improvement here. But now we can see much finer layers in the surface. We can see smaller rocks. We can see the shapes of the rocks and the surface textures, and we have the color here to help correlate the different layers and the compositions, which we can compare with the CRISM spectrometer that you'll hear about next. If I could have the next slide. This illustrates one of our main objectives, which is measuring the topography of Mars at very high resolution. And what we do is we point the whole spacecraft at the point on the surface from 2 different orbits, from 2 different angles. So we have parallax. That's the same way we see stereo with our eyes. And with this, we can derive topographic models with a meter scale resolution. And with such digital topography, we can do quantitative modeling of processes such as groundwater flow, gully formation, and viscous relaxation of topography, that is when there is ice near the surface. We can also use the topographic data to determine the 3-dimensional structure of layered deposits, to determine, for example, if it was deposited horizontally, as in a lake, or draped over pre-existing topography like airfall deposits, and as well as getting a much finer look at the polar layer deposits of particular interest for understanding climate change on Mars. So that's it for HiRISE.
And now to Scott Murchie, the principal investigator for the Compact Reconnaissance Imaging Spectrometer for Mars from the Applied Physics Laboratory. Scott.
Thank you. On behalf of the whole CRISM team of scientists and engineers who've been working very hard for the last 4 years to get to this day, I just wanted to say how excited we are to be just about beginning our journey to Mars. CRISM is like HiRISE in that it's a camera. However, it's a different kind of a camera that focuses on measuring color properties. CRISM is designed to measure the colors of the different kinds of minerals that make up the surface and map out the different rock types, and especially to look for the kinds of rocks that might have formed in past water environments on the planet. CRISM is not the first kind of a camera like this, called a spectrometer, to go to Mars. There's actually a spectrometer up there now on a European mission called Mars Express. The instrument is called Omega. And if you could go to the first slide, please. I'll show you an image that was taken by Omega. And this is the way we're used to seeing Mars in visible light. In visible light, everything is covered by a fine layer of dust colored by iron minerals. In the next slide, you'll see what Omega sees in the infrared. The infrared is a wavelength range of light past the red that's invisible to the human eyes, and it can see through that fine layer of dust at the underlying rocks that occur on the surface. And this is literally seeing Mars in a new light. And with images taken like this, we will be able to map out the distribution of the different kinds of rocks making up the surface. The next slide shows an overview of what CRISM will do once it's in Mars orbit. It will take two kinds of images. The first kind is a near global map that will show features as small as about 660 feet across. In those images, we will find new and interesting sites on the planet and go back and target them with the full spatial resolution and color resolution capabilities of CRISM. And in those images, we'll see features as small as 55 feet across, approximately the size of a house. And this gets us down to what's called the outcrop scale, where we hope to see the layers of bedrock cropping out at the surface, and we will complement the measurements of the layering and the morphology of the rocks by HiRISE by characterizing the kinds of minerals making up the rocks. In the next slide, you'll see how CRISM's results will compare to results from Omega, and the importance of the fact that CRISM will have a much higher spatial resolution. This is a simulation showing hot spring deposits on the Big Island of Hawaii. Now, hot springs are particularly interesting because they're a water environment, and it's also thought that 3.5 to 4 billion years ago, these are the kinds of environments where life may have begun on Earth. If Omega were to see a site like the Hawaiian hot springs, it would see something like in the left image, where the different colors represent different kinds of minerals. The middle panel shows what CRISM would see in its global mapping mode, and you can see that we can resolve smaller scale details, as well as in the upper right part of that middle panel, see deposits that were previously missed. The right panel shows a CRISM targeted image, and that's about the overall size, 6 miles by 6 miles, showing features as small as 55 feet across, and you can see the multiple deposits of water-formed minerals, distinguish the different kinds of minerals in blues and reds, and this helps to give you a detailed understanding of the geologic environment that formed the water-bearing minerals on the surface. So this will be a key part of the MRO mission in quantifying the characteristics of many sites for detailed future investigation. And that's the short story for CRISM.
We'll turn now to Enrico Flamini, the Director for Solar Systems Programs for the Italian Space Agency. Enrico?
Thank you. Well, I will present SHARAD. SHARAD stands for Shallow Radar. Essentially, is a radar that uses specially selected frequencies in order to penetrate the surface of Mars and searching and probing the deep part of Mars for looking for the water. May I have the first slide, please? Okay. And searching and probing, we are going to look which are the discontinuities in the subsurface layers. And in this sense, water both in solid and liquid form represent a huge amount of discontinuities, so the signal will be very, very evident. SHARAD is a facility instrument that's been provided by Italian Space Agency to MRO mission, and will complement the research that Mars is currently doing around Mars on board the Mars Express. May I have the next slide, please? And in the next slide, we can see the comparison between the two instruments. Essentially, as in the case of HiRISE, we are going to increase with a huge amount the capability of resolving both in spatial and in depth what Mars is currently already seeing on Mars. In the center of this image, in the central part of the image, show one actual signal received by Mars that show us that Mars's radar can penetrate up to 3 miles, that are 5 kilometers, while Charlotte will penetrate just about 1 kilometer. But the spatial resolution, I mean, the depth of Mars is only 150 meters, while Charade is able to resolve up to 20 meters. In other words, with Mars, we're going to have the broad picture of the distribution of water on Mars, while with Charade, we're going to have a defined picture, and mainly we will be able to provide the position, the depth, and the extension of the possible water layers that are ice or water layers, obviously, that are under the Martian surface, that are at the depth that in principle is reachable for future Mars exploration. This is which is the main goal. I want to thank particularly in the science team, and the team leader, that is Roberto Seu of University of Rome, that was not able to be here today, and but all the team that is made jointly by Italian American scientists, as well the Italian industry that provided the design and the manufacturing of this instrument, Alenia Spazio, with the support of a subcontractor on the American side, that is the Astro Aerospace, that actually manufactured the antenna under our specifications. And I want also to thank, finally, JPL and Lockheed Martin MRO team, which we worked very, very smoothly these years, and our friends at NASA headquarters that helped us in realizing all this second instrument around Mars. And at this point, I think that we are just looking forward for future discovery of other secrets of Mars, all together with this beautiful orbiter and experiment set. Thanks.
We're ready now for questions. Please give your name and affiliation when the microphone comes to you. We'll start here with Craig.
Craig Cavalt with Aviation Week. Rich mentioned that the importance of following up on some Odyssey results. Relative to Mars Express results so far, what are an example or two of some really interesting Mars Express results you'll be especially following up on?
I think Scott should
Do you want me to try that? First, the question was directed towards about the subsurface ice that Odyssey had found, or more generally? Let me give a start, and the guys can fill in here. On the ice, we're still just starting to learn how to interpret the subsurface radar data. The subsurface of Mars, we've literally scratched the surface, and we're trying to probe now more than a couple of feet into it at depth. And it's going to take us a while to digest what we see there, because it's not only dependent upon the composition, but on the structure of how those materials are put together. We got a lot to learn, and for MRO, we're looking forward to Charade providing, Marsis providing that first look at it so that we can fine-tune what we go and do with this. We have a lot of international cooperation between the teams, and one of the best examples of that, Scott, is your team with the Omega experiment. The leader of that team, Jean-Pierre Bibring, is a co-investigator, for instance, on Scott's team. And Scott, you might mention the site finding and such that you've already started to do.
Sure, thank you, Rich. Yeah, Omega has found some really interesting new findings on Mars. Earlier, you saw sort of a history of how we got to the Opportunity landing site, where there were discoveries from the Mars Global Surveyor and the hematite that resulted in a landing. Well, Omega is finding evidence for tens to hundreds of new sites where there's evidence for liquid water having acted on the surface, specific kinds of minerals like sulfates and clays that are indicative of different kinds of processes that form on the surface and that leave a mineral record that can go back and be investigated to give you information and insight into what Mars was like in the very ancient time, 3 to 4 billion years ago, when these deposits formed. Omega has been providing their early results to us, and we've already been going through the process of picking some of the sites that we will go back in our targeted mode to characterize at high resolution and get about 20 times higher spatial resolution than Omega was able to achieve. So essentially, Omega and CRISM are sort of a 1-2, logical first and second steps as part of an integrated investigation between the two missions.
I think that I could add something on that for what concern at least SHARAD. I mean, the PI of MARSIS is one co-investigator on SHARAD, as well the PI of PFS, that is the planetary Fourier spectrometer that is on board Mars Express, that is a co-I also on SHARAD, because we think that at this point in the history of the Mars knowledge is extremely important the interaction between different instruments and the interdisciplinarity in understanding better which is the situation. MARSIS has started to work only 1 month ago due to various reasons of delay. The data are extremely complex to be understood due to the fact that it's the first time ever with MARSIS that a radar, sounding radar, is flying on another planet. So we have to at first understand exactly how it works. But the data that we have received up to now are extremely encouraging us about what we had in mind that that radar should have done and that SHARAD will do on one side. And on the other side, I think that the MARSIS data for what concerns the other part of his main goal, that is the ionospheric sounding, are already providing us data that shows how the ionosphere of Mars is, I would say, more active than what has been expected. Obviously, these data are still under analysis, and the science team is trying to maintain this data still a little under control before publishing it.
Chris?
Chris Kreidler from Florida Today for Dr. Zurich. How will the weather observations on MRO improve upon what's been done with other spacecraft besides expanding the climate record?
Just as for the surface, we're looking to get more resolution in the atmosphere and also to survey when we produce a daily global map. Now we're going to do it in 7 colors rather than in just 2 or 3. And 2 of those colors actually would be used to trace ozone, which is anti-correlated with water. When water is present, ozone is not, and vice versa. So it's another way of following the water photochemically around the planet. With our sounder, we're looking to get better vertical resolution, and that means that by looking at the limb, we're able to look closer to the surface, and that's where most of the water tends to be in this rather cold atmosphere. So that'll be important for us to trace water around the planet, understand the interactions with the surface, and that's what we're after with that improvement in vertical resolution.
Here we have a question. Well, hang on just a second. We'll catch one right here in the back there.
Hi, Curtis Kruger, St. Petersburg Times. Could you talk about how the knowledge you gain from MRO will be used to support future manned and unmanned missions to Mars?
Well, there are several categories. When you're talking about human missions, just the planning of those, just scoping out what options you want to try, which direction you want to go in terms of the implementation, you have to know your environment and what you're working in. And it's also possible that you're going to use the atmosphere itself through aero capture or aero braking of large payloads down to the surface to provide an infrastructure for future humans. So that's one set of examples for it. Knowing what we're dealing with and where the resources are. For instance, is water ice close to the surface, and is there a lot of it? Could we get to that relatively easily? Because once you have ice, you can break that down into a whole variety of things. We don't want to be hauling cement to Mars. That's very expensive. Better to make and to know what we can make on the surface of the planet. Now, that's looking a long way out. I'll let Alfred here speak to what HiRISE, for instance, can do in terms of looking at sites to ensure that when we put down our very valued landers and rovers, that they're going to be able to do so safely as well. Alfred?
Okay, well, sometimes I think the main reason HiRISE is on the spacecraft is so the engineers can see those meter-scale rocks. Those are hazardous to landers such as Phoenix of that scale. And in the past, we've had models of rock abundance and extrapolations, and those have been fairly successful, but I think the engineers would be much happier if they can actually directly see those rocks. And as a geologist, I'm very happy to see them as well for other reasons. In addition, we can actually see the terrain in enough detail to make some pretty good estimations of how trafficable the terrain is for rovers. So we can really plan out future exploration on the surface in detail. And with the digital topography, we can simulate things and have what Jim Garvin once called 1,000 simulated landing sites on Mars. We'll also be very interested in looking at the past landing sites, both for ground truth for us, for understanding what we see, and for helping to interpret the results at those sites. And I have to break myself of the habit of calling MER a future past site because it may still be active, the Mars rovers, when we get there. So maybe we can even influence which way they go next to explore.
Leo M. Knight of Irish Television for Dr. Flamini. I was curious about the 1-2 symbiosis between Mars Express and this American spacecraft. Could I ask you about two specific instruments? First of all, the PFS aboard Mars Express. Is there something aboard the MRO that can help to resolve issues about Vittorio Formosano's results? And the second question has to do with these Marsus products that you showed us. I haven't seen any Marsus product before, and I'm wondering, is there anything in what you have seen so far in the first few weeks of looking at this that makes you say, yes, this particular area we would like to go to now with the new, more higher resolution instrument?
I will answer first the second question. And the answer is that the instrument is working pretty closely our expectation. I don't want to say much more about that, but it's working properly. So then obviously we have to clean up the data from spurious signal and from other sources like that, but it's very encouraging. And I think that in a short, we will have the clearance from the PI to provide this data, and so you're going to see more data with respect to what I've shown today. For what concerns the first question that I put a second part, I think that it would much better if Erich will answer that.
Yeah,
because
I can take that one because we don't do the trace gases that PFS is looking for. We don't do methane at the quantities that are reported. That's not what we're designed to do. The one trace gas that we do look at is water, and that is really what we're focused on. So we're not going to be able to confirm or not unless some of the very high amounts of methane that have occasionally been reported, we'd have a chance to maybe confirm that. But that's not the goal of our mission.
I could add just one thing to complete the scenario. The evidences that's been measured by Vittorio Formosano has to be further confirmed by further observation that hopefully Mars Express will do in the extended part of the mission. Increasing the amount of observation will get a better accuracy on the measurement. So this is what we intend to do.
I might follow up on that. There is one point that Mike had reminded me of here is that if you're looking for sources of methane, one of those is hydrothermal systems and such. And we are looking for those because those are the kind of materials that could provide a very good landing site for future missions, might preserve the kinds of things if life ever existed on the planet.
Are there any further questions? Craig, a follow-up.
Craig Cavalt, Aviation Week. I couldn't resist at the end here just asking for a quick update on Rover. I guess Mike Meyer, it appears opportunity is kind of out of the purgatory sandpit in the more flat pan, safer territory, and Spirit's about ready to peek out here. But if you want a sentence or two to address both rovers.
I must admit I haven't been paying attention the last couple of days just because of focusing on this mission that we hope to launch soon. But the rovers have had a rejuvenation with interaction with, we think, dust devils in which their solar panels have been cleaned off. And so now they have power approaching what they had to start with. And signs of being able to continue for quite some time. Opportunity is now headed off toward Victoria Crater as the ultimate goal, and it has a better understanding of the terrain that it's going across, and the terrain itself has gotten a little bit harder, so it's really putting in the miles. And Spirit is now kind of on the top of Columbia Hills and finding very interesting deposits there that are showing other ways in which we can find where water might have been on the planet. And I guess that's about all I can think of to say right now.
Any last questions? All right, a couple of programming notes. Launch coverage on Wednesday morning is going to be starting at 5:30 a.m. Eastern Time. That coincides with the start of cryogenic fueling of the Atlas V. And again, these briefings will be replayed today on NASA TV at 3 p.m. and 5 p.m. Eastern Time. Thank you very much. Boy, those rovers are the